Okay, now it's starting to record. Okay. So now let's start today's lecture. Okay. Before we go into the lecture note material, okay, I understand that many students are interested to know about the group project arrangement. Okay. So the group project you are going to do is not a big project. Okay. You can finish it. You will be given around a month to do the group project, okay? And we'll start with the course project registration first, okay? I will essentially set up a area in the Moodle for you to register your group, okay? The whole operation is like this, okay? A student will actually create a group in the register a group in the Moodle, and then the other student who is his or her team member will join the group join the group after that, okay? And the person who will create the group or on behalf of the group will set up a password to the group, okay? So only that group and other team member can join that group. Okay. Okay. So I will actually create a PDF to explain how the group registration process will be conducted. Okay. You will expect that the group registration webpage will be available on the Moodle on Wednesday. Okay. The whole idea is like this. Okay. I will create a web page to allow you to register your group. And after you form a group with a person, okay, your group will select a team leader, okay, and the team leader will be responsible to create a group entry in the group project registration webpage, okay. And when the team leader is setting up that group entry, okay, he or she will enter a password for that group entry, okay, and the group member of that group will enter the password and then add himself to that group entry, okay. So this is how the group registration system will work, okay. Essentially, it works by having a group leader set up a group account, and then the group members join that group account, okay? And to ensure that no other stranger will enter your group, you set up a password, okay? And the group project is very simple. It will be essentially a two-person project, okay? You need to form a group of two, okay? But the group project is quite simple. In fact, if you are confident enough, you can do it by yourself only, okay? You can request to do the project on your own, okay? Okay. I will set up the group registration page and start the group registration first on a Wednesday, okay? On around Wednesday, okay? And if everything goes well, I will create a PDF to explain how the group registration process to be done. Okay. Don't worry about it. You will be given around a month to work on that project. Okay. And essentially, the thing you need to do is to just the project's objective is to have a sense of how machine learning will work. Okay. In this course, we mainly focus on traditional AI. Okay. But I believe that many students are interested in how machine learning, that is the more popular paradigm of AI, is really works. Okay. But this course will not dedicate a lot of time on discussing the mechanism of the machine learning. Instead, I will give you a project and you will have a taste of how machine learning is supposed to work. Okay, so any questions? You may ask this, Professor, so if you do not discuss machine learning in this course, so how I can learn about machine learning? And in fact, in in the design of our program's curriculum, there is a dedicated course on big data analytics and machine learning. Okay, so you would be learning machine learning and big data analytics in those two courses. Okay, so in this course, I will take an approach that I will actually design a project that allows you to have a taste of what machine learning is supposed to be. Okay, and that will be, okay, you will learn more about the theoretical and the practical concepts of machine learning in the other courses in the curriculum. Okay, but in this course, because it is an introductory course, I still want you to have a taste of what machine learning is supposed to be. So the project will be about giving you first-hand experience on how basic machine learning is supposed to be. Okay, so any questions? Any questions? Any questions? If no, then let's get back to our lectures, okay? In the previous lectures, we actually first talk about A-star search, and we also talk about admissible heuristics, okay? So one thing you must remember about the admissible heuristic is that it always try to estimate the cost of the path to be lower than the actual cost, okay? If you have a heuristic that estimate the cost to be lower than the real cost, they will consider it as admissible heuristics, okay? Okay. And the one thing you must know about the A-star search is that the A-star search is selecting a node for expansion by this formula. Essentially, a terminal node in the search tree is actually representing a path from the initial state to that terminal node. Okay, and that node may get connected to the goal state in the future. So we take this formula. Essentially, we take two components. The first component is the accumulated path cost. That is real, okay? That is the real cost from the initial state to that terminal node, okay? And then we use the heuristic to estimate the cost needed to get from the terminal node to the goal state, okay? So by adding the estimated cost and the accumulated cost together, we actually have a total estimated cost from the initial state to the goal state that pass through the terminal we just working on, okay? And we can calculate these statistics, calculate this measurement for all the terminal nodes. And using this measurement, we can select the terminal node that works for us. Okay. And last time we also discussed how we go through we build A-star search tree. In fact, you only need to remember 3 steps. The first step is you calculate for each terminal node. You go from the initial state and you trace the path that can get to the terminal node, and you add all the path step costs together, and you get the path cost. And for the heuristics, you can use the heuristic function to get that value. And then you add that two numbers together, then the value would be the priority value. And that priority value will be used for selecting the node for expansion in the next round. Okay? We will essentially select the node that have the smallest priority value for expansion in the next round. Okay? You just mechanically remember those rules, and you can always construct the A-star search tree. Okay? Okay? And last time we also talked about some problems beyond classical search. Okay, so I don't know if you have learned this in DSE. Maybe I believe your curriculum have learned about this. Okay, but you may not. But some students may but some students you may not remember it exactly, okay? So this is called linear programming, okay? So in a linear programming problem, we essentially are given some criteria, okay? So essentially, no, this figure is what? Yeah, this one is better, okay? Okay. So essentially, we are given some constraint, okay? You are given two variables called x1 and x2, and they are larger than 0 and they are integers, okay? And then you are given a number called called z, okay? Ez, okay? And Ez is equal to 5 times x1 plus x times x2, okay? So you want to maximize the x value. And for maximizing the x value, the x1 and x2 have constraint. Okay, and these two inequality are the constraint that restrict the possible values for x1 and x2. And combined with the fact that x1 and x2 must be larger than 0, so we can construct a graph like this. Okay, in this graph, we actually draw the x1 plus x2 equal to 6, that is derived from x1 plus x2 less than or equal to 6. And then we put this x1 5 times x1 plus 9 times x2 smaller than equal to 45 into a line like this, okay? We put the line of 5 times x1 plus 9 times x2 equal to 45, okay? So we convert these two constraints into these two lines in our graph, okay? And anyway, and then we can establish an area, okay? And within this area, okay? And of course, because x1 and x2 is larger than or equal to 0, so you also constrain, you also impose constraint here and here, but it is too obvious, we don't draw it here, okay? So by visualizing those constraints into the graph, we actually establish an area that contains all the possible value of x1 and x2. And then for all the value of x1 and x2, we find a combination of x1 and x2 that will maximize our Ez value, okay? Our Ez value, okay? And you may ask is, Professor, so what is this related to search problem? So if we take the perspective of computers, the computer can solve this problem by jumping over all these possible x1 and x2 value points, okay? So maybe the computer can start with here where x1 and x2 is 0, and then it make a action and then jump to x1 and x1 equal to 0 and x2 equal to 0, x1 equal to 1 and x2 equal to 0, okay? And it goes on and goes on, okay? So the idea here is that the computer can solve this problem by exhaustively checking all the values in this area. Okay? Okay? It can jump through all the values inside this area. And if it come across an area that gives it the best possible x value, then it will return the x value. Okay? So if we actually take this approach, to solve the problem, we are actually talking about another type of search algorithms. In our previous search algorithm, we always have the goal state. We always have one goal state that is what we want, okay? But in a problem like this, we don't have a dedicated goal state, but we have a state that we want to find. The state we want to find is a state that has the highest value, the highest objective value. Okay, this Z here, the Z here is our objective value. Okay, and essentially we want to in this problem, in this problem, we are trying to find the combination of x1 and x2 that gives us the maximum objective value. And here the maximum objective value is the objective is the value of Z. Okay? Okay. So when we are talking about single state problem, we have the goal test. Okay, we have the goal test that dedicatedly tell us when to stop. And now we need to come out with another mechanism to stop our search, okay, and to return the final result. And that is the three kinds of search we will need to talk about. Okay, the major differences of the free search algorithm we talked about when compared to the existing search algorithm we talked about before is that in the past we search for one goal state and we'll stop whenever we reach the goal state. Okay, but now we don't have a dedicated goal state, but what we want to do is to find one state that gives me the highest possible objective value. And that objective value is separately defined by a function. Okay? Okay? So any questions? Any questions? Any questions? But you may say that, Professor, I learned this in DSE mathematics, so I learned it in A-level mathematics. I know that I don't need to exhaustively check all the solutions to find the optimal value.
Use the vertex.
Yeah. But why you will teach us using computer to exhaustively find the solution for us? The reason is simple. In the real world, you have far more constraints you need to work with. Okay? If you have more than one variable, we have two more variables. Okay, for example, if you have 4 variables, then the dimension of the graph you work on is 4. Okay, I don't know about you, but if my understanding is correct, human beings cannot visualize dimension more than 4, more than 3.
Yes.
Okay, human beings have difficulty visualizing the dimension that is bigger than 3. Okay, so if you have like 10 variables I need to work with in my optimization problem, then this approach of drawing graph and then sliding the front end, sliding a line to get to the optimal solution doesn't work. It makes sense, right? It makes sense, right? So if you have more variables, if the constraint we're working on is more difficult, is more complicated, then this approach would not work. This approach relies on the visualization of the constraint in a graph, and then you manipulate a line in the graph to find the solution that you want. So for your DSE mathematics and integer programming solver to work, you rely on the visualization. Okay, but if we are working with more variables, more than 3 variables, then you cannot visualize it. Then your whole approach would not work. In computer science, we will say that your approach cannot be scaled up.
Yeah.
Okay, so that is why we will need to talk about new techniques that is able to find the optimal value of a problem under more than, like, for example, 10 variables. Okay, so how we achieve it? We'll briefly talk about the algorithm you can use to solve that problem. Okay, in fact, in the future, okay, there are other courses that will talk about those methods as well. Okay, so that is why I will actually take a more introductory conceptual discussion for all these algorithms, okay? First, the first approach is called hill climbing, okay? Fundamentally, it is quite similar to the linear programming visualization technique you use. So we gradually move to the top, and then when we get to the top, we stop. Okay? So to illustrate the concept more easily, we use this diagram to illustrate the concept. Okay? In this diagram, the y-axis is the objective function. So it actually talk about the objective value of the state. Okay? And the x value and x-axis is the state space. Okay, we reduce the problem into only having one variable for easy discussion. But the idea can always be scaled up to handle more variables. Okay, the reason why is that we actually generalize that the action of finding the next variable configuration for exploration as finding the neighbors. And the action of finding the neighbors is upscalable to a dimension that is bigger than 3. Okay, you can always find a neighbor of a vector no matter how long the vector is.
Yeah.
Okay, so in this approach, we actually try to abstract the concept of finding the next configuration as finding the neighbors. Okay, so this approach would work even if you are working with more than one dimension. Okay, but for the sake of discussion here, we configure our problem only have one dimension. Okay, and because the dimension is only one, we only working with one variable, so only using one axis. Using only one axis in the graph is enough to represent the state of our problem.
You mean you treat the xy coordinate as one as the state space, like
Yeah,
xy one.
the x-axis is the state space and the y-axis is the objective function. Okay, so this chart is actually visualizing the relationship of the objective value against the state of the problem. Okay, so the curve you see in this graph is actually visualizing what objective value you are going to have given a state. Okay, so for example, if the state of my problem is right here, then I draw a straight line up touching the curve, and I draw a horizontal line touching the objective function axis. Then I know the objective value of this state. Okay. So this is simple technique of reading a chart in mathematics. Okay. So the x-axis is representing the state of the state of the problem. Okay. So any points in the x-axis are actually representing a possible state in the problem. Okay. And the line in the graph is actually representing the relationship of each state in the problem against the objective function. So if given any point in the state space axis, for example, right here, if I want to know the objective function value of this state, I can move upwards touching the chart, and I move horizontally to the objective function, and now I get the objective value of that state. Okay, simple chart reading technique. Okay, so in a problem like this, if we are going to search for the optimal value using the hill climbing algorithm, what we need to do is to randomly start our search at a position. For example, we start our position right here, okay? So now we start our search right here in the mouse cursor I'm pointing to. And for this state, it has two neighbors, okay? It has the neighbor at the left and the neighbor at the right. Okay, because we are working with one dimension, so we only have one neighbor. Okay, only have neighbors from two directions. We have the neighbor at the left and we have the neighbor at the right. Okay, and if we move to the right, if we move our state to the right, okay, if we move towards the right state, okay, then the objective value according to this curve will be increasing. Okay, and this actually satisfied our expectation. It actually is what we want to do, because in this problem we are trying to find the maximum objective value. We are trying to find a configuration of X that can maximize the objective value. So moving to the right can actually give us a better objective value. So we'll move to the right. Okay. And as the agent keep doing this, okay, it will essentially reaches a point right here of my mouse cursor. Okay, right here as my mouse cursor. Okay, right here as my mouse cursor here. That okay, my right here. Okay, right here that my mouse cursor has highlighted that the moving left and moving right doesn't increase the objective value, doesn't give us a better objective value. So at this point, we can stop. So this is how hill climbing supposed to work. Okay, but the issue of the hill climbing is also very obvious, as we already point out. When you do the search in this manner, then you can actually get stuck in the local maximum. Okay, local maximum refers to a peak of objective value that is better than other surrounding state values. Okay, so if you are running hill climbing, if you get stuck at the local maximum because the hill climbing doesn't have the overall understanding of the whole state space. Okay, it only knows the objective value of the neighboring state. So if you're stuck at the local maximum in the hill climbing algorithm, you will never escape from the local maximum. Okay, so that is the issue of hill climbing. You try to optimize the value just by comparing the value now and the value of the neighbors. Then you don't have the overall global perspective of the problem, and as a result, you will stuck at a local maximum. Okay, and that is the reason why we have other search algorithms. Okay, because hill climbing algorithm, just having a hill climbing algorithm is not enough to solve our problem. Okay, because it have the potential to get stuck at local maximum. Okay, or local minimum. Okay, so any questions? Any questions? Okay, let's continue. Okay. And the next technique that we talk about, and we also talk about different variants of the hill climbing algorithm, okay? Though the description is right here, we have already discussed in the previous lecture, so we can stop as well. And the last time we also talked about simulated anyway. In the simulated anyway, we essentially changed, we essentially do two modifications to the hill climbing algorithm. In the hill climbing algorithm, one important issue that we have done is that we use the differences of the objective value of the current state and the neighbor state as the stopping condition. Essentially, we stop the search whenever the current state that we are having now is having a better objective value than all its neighbors. Okay? If in hill climbing algorithm, if we found a state that its objective value is better than all the objective value of other neighboring states, then we stop. Okay? This is the stopping condition of the hill climbing algorithm. Okay, so that is why we will say that the hill climbing algorithm is only considering localized information and it cannot get to the goals to a global maximum or global minimum. Okay, but for simulated anyway, we do something quite different. Okay, and simulated anyway is actually trying to simulate a process called anyway. Okay. So when you are working in the metal forging, okay, essentially when you are working with metalworks, okay, if you are working with the manufacturing of knives, okay, the manufacturing of kitchen knife, for example, okay. If you are working with metal processing, okay, you will want the metal to be strong, to be able to be durable. Okay. For example, you do not want your kitchen knife to the edges of the kitchen knife to go back with just chopping 1 to 2 bone pieces. Okay, it makes sense, right? It makes sense, right? So to increase the strength of the metal, one way you will need to do is that when you heat up a metal in high temperature, such that it is soft enough for you to manipulate it, for you to forge it into the shape you desire, then what you need to do is to get that metal slowly cool down. Okay, the slowly cool down process of the metal would allow the atoms to get into the correct structure alignment, okay, such that it can give the metal the highest strength, okay. When we are creating the simulated annealing algorithm, we don't actually care about the metal crystal, metal atom alignment, okay. We only borrow the concept of cooling down. Okay, we actually borrow the concept of cooling down in our design. So when you see the simulated annealing algorithm, we introduce a new variable called the time. Okay, the time is actually starting from a very high value and gradually decrease to 0. Okay, we are borrowing the concept of temperature. Okay, from the actual annealing process. Okay, we set up the temperature and it is a very high value, and this value will gradually decrease to until it is 0. Okay, so when it is 0, then we will stop the search. Okay, and the temperature decrease, and the temperature is used as the indicator, is used as the figure to indicate how active we should be when we are allowing the algorithm to make a bad move. Okay. The second concept of the symmetric annealing you must know is that when you are doing symmetric annealing, you would introduce back move. Okay, by allowing back move, you allow the search algorithm to be able to have diversity and jumping away from the local maximum or local minimum. Okay. And the temperature is used in our calculation to indicate how likely we should allow a back move. Okay? Okay? And the concept is that in the current state, you first get all the successor or neighboring states, okay? And you randomly choose a neighbor, and you randomly choose a neighbor among all the neighbors that you have. And then you check out the utility values, the objective values of the neighbor against yourself, against the current state, okay? And you get a delta value. If the delta is larger than 0, that means that the next move is a good move. It can increase, it can make the utility value better, so we'll jump to that state. Okay? And on the other hand, if your delta is more than 0, then you will actually create a probability threshold. And the probability threshold is calculated using both the delta and the temperature. Okay? And then we'll randomly generate value to see if the randomly generated value is higher than the threshold that we specified. If your threshold value is smaller, that means that it is more unlikely that you will be able to satisfy to make this condition become true. So it is less likely to take a bad move. Okay? If the delta is more than 0, that means that the next is a bad move. That means that the next is a bad move. Okay? If next is the bad move, okay, so we can interpret this else if statement as we check whether the random value is exceeding a threshold. Okay, if the value is exceeding a threshold, if the randomized value is bigger than the threshold, then we take the bad move. And if the threshold here is smaller, that means that we have a smaller likelihood to go to make a bad move. Okay? Okay. So let's visualize the changes of this threshold against the temperature. So this diagram is actually visualizing the changes of the threshold of the probability threshold starting from temperature of 100 to 0. Okay. And as we decrease the temperature, the value of the threshold is also decreasing. Okay. Okay. And one thing you must notice is that the delta E is naturally negative. Okay. The delta E is naturally negative because you will trigger this calculation only when the delta is not positive. Okay. So this calculation is only triggered when delta is negative. Okay. And a negative value divided by temperature. Okay. If the temperature is bigger, that means that this negative value is smaller. Okay. This negative value is smaller. Okay. If that negative value is smaller, okay, then the threshold is bigger. Okay. If the negative threshold there, if the negative threshold is bigger, okay, if the negative threshold is bigger, that means that if the negative value in if the delta is negative, if t is smaller, that means that the delta divided by t is bigger, okay? Because this is a bigger negative value, so the equilibrium number powered by a bigger negative value means that it will be closer to zero, okay? So as a result, the threshold is smaller, okay? So you can see one trend here. As temperature decrease, the threshold is smaller. If the temperature is bigger, then the threshold is bigger. Okay. Okay. So we use this function. We could do this equilibrium number powered by the delta divided by t. We use this as the threshold, and we are essentially controlling the threshold of doing a bad move. Okay, if the temperature is bigger, then the threshold is bigger. If the temperature is smaller, then the threshold is smaller. Okay. Okay. And you may ask this, Professor, so why I just use the temperature here as the just why I don't use the temperature as the decisioning factor? And the reason is, to be honest, is implementation differences, okay? If you come up with another function that can control the descending trend or the threshold, then you will have a different search algorithm behavior, okay? But the overall major concept here is that as the search goes on, the probability of the bad move allowed should be decreasing. Okay. The idea of why we allow the bad move is that if in this problem, okay, it is similar to the previous example here. It is similar to the graph here, but it is similar to the graph right here. Okay, we have the x as the state and the y as the objective. But now in this diagram, minimum value here means beta. Okay, so objective value is smaller means beta. Okay, and in this problem we actually see one behavior. Okay. So if our algorithm gets stuck in the local maximum, okay, as a local minimum, okay, the allowing bad move design will allow it to jump away from the local minimum. Okay, it allows it to have the chance to jump from the local minimum. Okay, okay. But you may ask this, Professor, so if bad move allow the algorithm to jump from a local maximum or minimum, so why we want to decrease the jumping action throughout the search? The idea is simple. If your search is long enough, your algorithm, your state should be able to locate a state that is close to the global minimum. Okay, if the search goes on for a long time, your algorithm should be able to find a state that is very close to the global minimum or global maximum. If you still allows the algorithm to make a lot of bad moves, then you'll be jumping away from the global minimum, and that is not what we want. Okay, we want the algorithm to stop right at the global maximum or global minimum. Okay, so at the later state of the search, we would assume that the algorithm should be quite close to the global minimum in the best case scenario. So we don't want to do a bad move to make it jump away from the global maximum or global minimum. So that is the reason why we gradually decrease the amount of bad move allowed. Okay. Okay. And in this graph, you can see that at the beginning of the threshold is decreasing very slow. and at the end it decreases very fast. Okay, this shape will actually allow our search algorithm, okay, to do a lot of bad move at the beginning of the search to avoid it getting stuck to the local maximum, okay, or local minimum, okay. But at the end stage of the search, the bad move is drastically decreased such that it can get locked to the global maximum or global minimum. Okay. So any questions? Any questions? Any questions? Any questions? Any questions? Any questions? And you may ask is, so Professor, so all these algorithms, okay, they are useful, but why we want to learn it in the first place, okay? And in fact, the reason why you want to learn these kinds of algorithm in the first place is that in the business world, you sometimes need to do optimization. Okay, essentially, when you're designing a product, or if I am trying to plan out an action, I always need to do optimization. I always want to minimize my cost and maximize my profit. Okay, this is what AI, one major application of AI in the world of business. Okay, we always want to minimize the cost and maximize the profit. Okay, and if you want to minimize the cost and maximize the profit, then it becomes a search problem that try to find the best possible objective value among a bunch of configuration. So that is the reason why you want to at least know these kind of algorithms. Okay, and but you may ask it, Professor, so but if this is important, so why you only spend around like several pages to describe this algorithm, okay? And the reason why is that in the future, you'll be taking some other courses that will go into the more rigorous discussion on all these techniques, okay? You actually have a course called optimization in our curriculum, okay? So if you are interested to learn those techniques, you are recommended to take that course. Okay. So in this course, okay, I'm just giving you a general concept on what kinds of algorithm you can use to achieve the problem solving in the business world, like finding a configuration of product that can minimize the cost and maximize the profit, something like this. Okay. Oops. And the next algorithm we need to talk about is genetic algorithm. Okay. And also one thing is that optimization problem is still not a problem easily solvable by ChatGPT or large language model right now. Okay, large language models can only generate a piece of text based on your input. Okay, when you input your question, the ChatGPT will generate the response according to how likely humans will reply to that question. Okay, so it is based on the probability distribution of the word association in human text. Okay, and as a result, large language models is not quite capable of doing optimization that essentially is finding the optimal value over a bunch of configuration of variables. Okay, this problem is not quite efficiently solvable by large language models. So that is the reason why you will want to learn them as well. Okay, ChatGPT and other large language models, they are not the silver bullet for solving any kinds of AI problems. If you want to find the optimal value of a configuration of variables, of a bunch of variables in to optimize the profit and minimize the production cost of a product, then this kind of search algorithm would be essential for your problem solving. Okay, and large language models will not give you a good answer because the model nature doesn't allow it to achieve this task as efficiently as you believe to be. Okay, so any questions? Any questions? Any questions? Any questions? And the next algorithm that we want to talk about is genetic algorithm. Okay, where in the simulate anyway, okay, we are trying to cover the search space as much as possible. Okay, but clearly we cannot cover all of them. Okay, we are essentially trying to cover it as much as possible according to the temperature decreasing trend. Okay, and we have another algorithm that can do the searching for us. Okay. Remember when we are talking about the solving, when you are trying to solve the linear program, we are finding a way to explore all the possible variable configuration that is available, and we find the maximum value. Okay, and we have been talking about two different ways to do so, and the third way is quite different from the design. No matter it is simulated anyway or hill climbing, okay, they all depends on checking out the neighbors. So in the hill climbing, you essentially check out the neighbors, and you go to the neighbor that gives you a high value. And for simulated anyway, you do the same, you check out the neighbors. But in the genetic algorithms, we actually take inspiration from the natural world. Okay, we actually try to consider the configuration of variables as the chromosome of an organism. Okay, we essentially consider the configuration of a problem, a configuration of variables, configuration of values of a bunch of variables as a vector. Okay. If I draw it as a vector, then I can kind of consider it as the chromosome of an organism. Okay. And if I do this representation, I can consider the search of the optimal configuration of variables as finding the organisms that have the highest utility. Okay, so essentially what we are trying to do is to simulate natural selection. The core nature, the core principles of genetic algorithm is that we try to simulate natural selection. When we are working with natural selection, this is how nature works. Okay, the organisms, they are, in order to survive in the habitat, okay, they will actually do crossover breeding to generate a lot of new organisms. Okay, and the organisms that survive the environment will be able to reproduce. Okay, so the process of natural selection is that for organisms that is fitting to the environment and can survive in the environment is allowed to reproduce and to generate a new generation of the organism. And as this goes on and all goes on, only the organism that is the fittest to the environment would be able to survive. Okay, and the genetic algorithm is borrowing the concept of natural selection into the algorithm design. So imagine this: we can consider the objective value as the fitness of a solution. Essentially, we can consider the objective value as measuring how fit the solution is in solving the problem, and the problem itself become the environment that the solution need to survive from. Okay. So this is the nature of the problem we would need to work on. Okay. And once we have this thinking, we consider the objective value as how fit the solution is able to solve the problem. We can consider the solution itself to be an organism in the environment. Make sense, right? Make sense, right? So let's consider this. When you have a solution to a problem, for example, a configuration of variables, okay? If its objective value is higher, that means that that solution or that configuration of variables is able to solve that problem better, right? Okay. So if we consider the problem that we want to solve is the environment, okay, and the solution that we have generated is the solution we want to generate. The solution we want to generate is the organisms living in the environment. Okay, then the objective value of the solution is essentially representing how good the solution can live in the environment. Okay. Let me repeat, okay? I understand that it is very complicated to understand. So in biology, you learn that the organisms are surviving in the environment with the natural selection paradigm. So the core concept is that an organism, when it reproduces, it will reproduce a lot of offspring. And the offspring that fit the environment can survive, and the offspring that doesn't fit the environment cannot survive. Okay? And the organisms that fit the environment can then be allowed, can then remain to reproduce. Okay? So this procedure keeps on going, and you have organism that is getting more and more fitting in that environment. Okay, you have organism that is more and more fitting to live in that environment. And if we consider the problem we want to solve itself as the environment, okay, and the solution that we want to generate is an organism living in the environment, that is the problem, okay? Then the objective value of the solution can be a measurement indicating how fit that organism is living in the environment, right? So it makes sense, right? It makes sense, right? Okay. So if we consider the problem we want to solve as the environment, and the organism and the solution we want to generate is the organism. So if we take this analogy, okay, then finding the best solution for the environment, that is the solution with the best utility value in the problem, will be transformed as finding an objective that has the highest fitness value, indicating how fit it is in the environment that is living in. Okay. Okay. So the genetic algorithm is taking this analogy in the algorithm design. We first generate a bunch of candidate solutions. Okay. And the candidate solution is essentially a configuration of the variables that we randomly assign value to. So for example, if we take the egg queen problems in the past into our discussion, okay, we can actually generate a vector where each value in the vector is indicating the positioning of each queen in each column. Okay. So for example, the first value in the column is indicating the row positioning of the queen in the first column. Okay. And the second value in the vector is representing the positioning of the queen in the second column, and so on. Okay. So using this representation, you can actually represent a configuration or state of our problem as a vector. Okay. And this vector, you can consider it as the chromosome of the organisms in our genetic algorithms. Okay. And initially, we randomly generate a bunch of candidate solutions as the chromosome of a bunch of organisms. Okay. And for all these organisms, we evaluate how fit they are. Okay. Regarding to problem, essentially we calculate the objective value of those organisms, of those solutions towards our problem. Okay. And only the solutions that have a higher value, that have a higher objective value, are selected for mating. Okay. This part is emulating the natural selection. Okay. In natural selection, the organism that do not fit the environment will die and they never get the chance to mate. Okay. And in our algorithm, when we are evaluating the fitness, evaluating the objective value of each solution, we are facilitating the selection of good solution for breeding the new individuals, for breeding the new solution. So essentially, this step is to simulate the natural selection. Okay. And then the next part is that we try to generate the offspring by crossover and mutation. So the crossover is that we try to split the vector of both solutions into two halves, and then we swap it. Okay, like crossing over a chromosome in real organisms. Okay. In fact, you can consider the crossover action of the genetic algorithm similar to finding the neighbors of the current state. Okay. Okay. Essentially, what we are doing here is that we take the good candidates, we take the solution, we take a candidate solution that have a better objective functions, and then we try to split the solution vector into two halves for that candidate solutions, and we swap them, okay? And we swap them like you see in diagram, okay? You can see a diagram, the diagram is more illustrative than my mouth, okay? So you can see here, we start with two candidate solutions that is having a higher objective values, and we do a chopping. We chop the candidate solution vector into two halves. For these two candidate solutions, we have four segments in total, and then we combine them to generate two new candidate solutions. Okay. This part is similar to the crossing over of the chromosome when two organisms is doing reproduction. Okay. Okay. So that is why we label it a crossover. Okay. Essentially, this step is fundamentally similar to finding next candidate state in the previous algorithm we have been discussing. Okay, fundamentally similar. Okay, the idea is that if we have good solution, and if we are generating a good solution by recombining the good solution together, then you can come up with even better solutions. Okay. Okay. So for example, okay, if you are working on a research, okay, when you're working on a research, okay, you can actually of course with citation, okay, you can try combining the different techniques from different papers to generate a even better algorithm. Of course, with citation, of course, okay? Okay. Okay. If you found technique A that is good, and if you found technique B that is good in two different papers, after proper citation of these two techniques, okay, you can merge them together to form a novel newer algorithm. Okay, and you can consider crossover is similar to that. We are using the good solution that we have, and we mix and match together to generate potentially better solution that can solve the problem even better. Okay. Okay. But one problem we need to work on is that similar to the third problem we have been talking about. If your solution is clustered right here, okay? If all your solution is clustered right here next to the local maximum or local minimum, then no matter how you do crossover or mutation, no matter how much crossover you are doing, you will get stuck right here. You will start right here at the local minimum. Okay. For example, if your solution is stuck right here in the area I highlighted here, okay? If all your genetic algorithm solution is in this region, in the region that I highlighted here, okay? Then no matter how you do crossover, you always get stuck. Okay. So the next idea is called mutation. In mutation, we essentially just select one value in the solution vector, and we change it randomly. Okay, changing the mutation operator by randomly changing a value in the vector, you actually facilitate a potential move that can jump from the local optimal, or local maximum or local minimum. Okay. For example, if you, for example, right here. Okay. If you start right here, but you do a random mutation and then you jump right here, okay? Then you properly can move away from the local minimum. Okay? So any questions? Any questions? The local, or you can say in this manner is that if you just do crossover, then you are just exploring a tiny proportion of the surface space. The mutation allow us to force the algorithm to explore a bigger space. Okay, so it can force the algorithm to try to explore other aspects of the surface space, and hopefully we can hit the global maximum with a higher chances. Okay. Okay. One thing you must know is that genetic algorithm is random by nature. Because you have the mutation, you start off with random generation of the population, and you also have random mutation. So the nature of genetic algorithm is random. Each time you can get a slightly different result when you execute it, okay? And it is not guaranteed to give you an optimal solution as well. But in situation where it is very difficult to find an optimal solution, okay? In a situation that it is very difficult to find an optimal solution. If the surface space is so large that it's very difficult to find an optimal solution, then genetic algorithm, it will be a good thing to do. Okay. And one last step is that you will only keep the individual that have a bias to the good fitness. You essentially only keep individuals that have a good objective value. Doing this step allows you to force your search towards the global maximum or global minimum. Okay. And this part is also simulating the principle of the fitness of survival of the fitness in the natural selection. Okay. And you may ask this, Professor, so how the genetic algorithm can stop? When we are running genetic algorithm, we will actually predefine the number of iterations we will want to generate. For example, we will limit the genetic algorithm to only run for 100 or 10,000 generations, okay? If after generating 10,000 generations, then we'll stop, okay? Okay? Okay. And of course, and one thing you must know about genetic algorithm is that there is no guarantee you can always get a global optimal when you are working with genetic algorithm, but you can at least get a quite good local minimum or local maximum using genetic algorithms. Okay? So any questions? Any questions? Okay? So if there is no question, so we'll stop right here. And in the next lecture, we'll actually go to talk about one new topic, okay? Gameplay. So we'll actually talk about how computer is able to play chess. So we will not go into the heuristics of AlphaGo because they are very involved, but we will at least talk about the backbone of the design of the chess playing AI. So one thing essential is that the chess playing AI is doing the same thing as what the Doctor Strange have done in Avengers 3 movie. Okay? In Avengers 3 movie, Doctor Strange need to find a way to defeat Thanos. And his approach is very simple. He used his ability to explore all the parallel universe and go through each one and find one universe that they can win. And Doctor Strange can guide all the Avengers to try to get to that universe. Okay. Essentially, ChatSpace AI is doing the same. The ChatSpace AI is able to compute all the possible scenarios that can happen in the whole game. According to the rulebook, you know that player A has X move, and then substantially the player Y has N move. Okay, you can list out all the possible combination of the rules and the turns in a bunch of sequences. Okay, and the computer check each sequences one at a time to find one sequences that it can win. Okay, and it will try to make move that force the human player to go to that route. Okay, so that is what I would say. The game of AI playing chess is substantially similar to how Doctor Strange helped the Avengers to defeat Thanos, because it is doing the same thing. I list out all the possible scenarios, all the possible development in the game, and I select one round that make me win the game. Okay, that is actually how simple it is. And we'll talk about the algorithm that help the computer to generate these sequences very smartly. Okay, and this will be the next lecture topic, and they will be discussed on Friday. Okay, I will actually release the group project registration page on Moodle on Wednesday. Okay, the group project will be a 2-person group. You can choose to do your group project with 1 person as well. Okay, I will actually release a PDF that describes how the registration process should be done in the Moodle. Okay, so any questions? And you have a one month to work on your project, so you don't need to be very afraid of the project. Okay, and the project is to give you a taste on how machine learning would work with simple graphical programming toolkits. Okay, so this is the end of today's lecture. I will need to end the lectures now, such that I don't